I'll start recording. Right, so here's a kind of where we stopped, or what we went over last in the last lecture. So we looked at what the effective interest rates are for a given time period, and then we said you can identify the payment period and identify the interest period. And sometimes those are going to be different, and sometimes they're going to be the same. And then you may need to do some conversion in order to make these two match. Okay? And then after that, you can carry on with your calculations the way we did in chapter 2 and the way you guys did in the quiz, right? Using the formulas that we've covered. It's just that you need to find the right I and you need to find the right N. Okay? And we said there are two cases, either the payment periods and the interest periods, or the compounding periods. They coincide. That means they're the same. And that's the case where C is equal 1. Remember, C was the number of compounding periods per payment period, right? So if you have those two match, that means you just have exactly one compounding period in a payment period. The other case, of course, is where they differ, right? And we saw the first case together. We said C is equal 1 when they coincide. And the way you solve problems like this is, as I said before, you need to find I, you need to find N. And the way you find I involves finding M. So that's step 1, right? So I is a function, I guess, of M. You can think of it this way. So you first find M. M is equal to CK. Of course, when they coincide, C is 1. So M is equal to K. What is K? K is the number of payment periods per year, right? So you find what K is, then that gives you M. You divide your interest rates, the nominal R, you divide it by M, and that gets you I. And then you find the total number of payment periods, capital N, which is M times the number of years, right? So M is per year, and then you multiply that by the number of years, and that gives you the total number of payments, capital N. And then you use the formulas that we had in the formula sheet, for example, to compute what you want to compute. And we saw an example of that with the car loan, so I'll just skip over this. And so today we're going to start from case 2, which is when these two things differ, right? So it seems like maybe we're because we spent a lot of time discussing the quiz, that we're going to be we're not going to finish this today, so we can finish it at the start of next class, and that's fine. So in this case, the payment periods differ from the compounding periods. The overall scheme or steps are the same, right? In step 1, you identify K and C. K is the number of periods per year. C is the number of interest per payment period. And that actually gives you M, right? So M is equal to C times K, right? And then in step 2, you compute the effective interest rate using the formulas that we've covered before. If it's discrete compounding, you use this formula. If it's continuous compounding, remember this is the case where C goes to infinity, then you use this other formula that we derived. Okay, and so you have C now, you have K, which is M. You can write this as M if you want to, or you can just keep it as CK, and you raise to the power C. And you find the total number of payment periods, right, which is just capital N, and then you plug in the formula for. So this is not really a big change from the first case. That one was just where C is equal 1. This is a little bit more general, but the overall framework is the exact same. You find the parameters, find the interest rate, find the correct N, plug in the formula. Okay, and so here's an example on this case. So let's suppose I have this cash flow pattern, and I'm paying A is $1,000. I'm paying so A, remember, stands for like an equal payment series. So I'm paying this amount, and I'm paying this amount every quarter. So in a given year, for these 3 years, I'm paying 4 times, right? So I have 4 payment periods in a year, right? What does that give me? 4 payment periods in a year. What parameter is that?
C.
C.
Actually, K. So maybe this will take some practice. So K, or did I get it backwards? No, it is K, right? So K is the number of payment periods per year. And so I have 1, 2, 3, 4 payment periods per year. So that's what K is. C, remember, the way to remember this, C stands for compounding. So C is how frequently the interest is applied. And up to this point, I didn't say anything about the interest yet. I mean, I just said you have $1,000 paid in each quarter. So you do it 4 times a year. So K is equal to 4. Okay? And so we'll get to C, actually. I think C comes next. So this is, oh, here we just skipped straight to M for some reason in the slides. So remember, M is C times K. K, I already told you, is 4. And so, of course, I mean, you know what M is, so you can figure out C. But C, if you think about it, well, C, I'm given a nominal interest rate, 12% per year. It's compounded monthly, right? So I'm applying the interest every month. My payment period is a quarter. So that means I'm applying the interest 3 times in my payment period, and that's what C is. So C is equal to 3. Okay? And then M is just the multiplication. So that's why you get M is equal to 12 periods. And if you think about it, M is how many times you apply the interest per year. And so because I apply the interest 3 times in every quarter, I have 4 quarters. I'm applying the interest 12 times in a year. Okay, so hopefully you all follow this bit. What is N? I mean, you can see here from the cash flow diagram, I have 12 payments. So N is just 12. Or you can take K, the number of payment periods per year, and you multiply by the number of years, which is 3. So 4 times 3 also gives you 12, which is exactly what we see in the cash flow diagram. And in this question, we're asked to find the future value, the future worth of this sequence of payments. And so first of all, I recognize that this is a discrete compounding scenario because I'm compounding monthly, right? I'm not compounding infinitely or anything like that. It doesn't say continuous compounding, so this is discrete. And so we can look at this example, for example, assuming, first of all, assuming monthly compounding, which was given in the question, and then we're actually going to look at it assuming continuous compounding. So the first case is discrete because we have monthly. The second case is going to be continuous compounding in the next slide, just to see how the numbers compare. We've already found K and C. I plug in the formula to find the interest rate, the effective interest rate. So that's the second step. And so I have C, I have K, I have C. And that gives me the actual interest rate that I should use in my formulas. Okay? What's next? I need to find N. I already did. N is equal to 12. I have 12 payments. I need to find the future value. So I need to find F given A, because this is an equal payment series. And I plug in the correct interest rate, and I plug in the correct N, which I've just computed, right? So this one here and this one here. I plug in the formula. You already know how to do this. So my A is 1,000, which was given. And I get the final answer, 216.24. So that's the future value of these payments. Okay. Let's look at the case where we have continuous compounding. Same parameters, same example. It's just that we're changing one parameter, actually. One parameter changes, and that is how frequently we apply the interest. And so what parameter is going to change?
The C would be infinity.
Exactly. Right. So in a way, C would be infinity. K stays the same. I don't change the number of payments that I make in a year. I apply the formula. Of course, the formula doesn't really have C because C is infinity. So I have, remember, the formula for this case is E to the R, the nominal, divided by K. I have K is equal to 4. I have the nominal. I plug in. I get my interest. So the interest is also going to change. Look back at the interest here, 3.03, 3.045. So it's a little bit higher, which is expected because you're applying the interest more frequently. So that's like a nice sanity check to make sure our answer makes sense so far. N is not going to change. I'm still making the same number of payments. I apply the formula now with the new interest rate, and I get the answer. And just to check again, I go back here, 14,216, 14,228. So it did increase, which is good because I'm applying the interest more frequently. And that means at least my answer is not incorrect. Like I can't easily tell it's incorrect just by looking at the answer. All right, so hopefully this example makes sense now. And it helps you make sense of the concept of effective interest rates. Here's another example. Suppose you have the following cash flow pattern, and you're asked to find F again. The only difference here is that the interest rate is changing. If you look at the example, you have 3 payments total. In the first 2 years, I tell you that the interest rate is 8% compounded annually. In the second 2 years, it's 6%, but now it's compounded monthly. So that's a big, it's not only a difference in the number, notice it's also a difference in how frequently you apply the interest. All right, N is equal to 4, which I can tell from the graph. Find F. Okay, So how do we handle problems like these? Even just from chapter 2, what's the principle here when you have changing interest rates? How do we do this? Yes, Muhammad?
We can deal with it as two separate periods and then add them up.
Exactly.
Oh.
So you can break the problem down into 2 periods, and that's exactly what we're going to do. So the first one is this part here because it has its own interest rate, and then the second one is this part here. And in fact, I can move this payment on its own here, and then add the 150, and then take them together and move them here, and then add the 450, right? So that's how like the slides have it. So the first thing is we're going to look at years 0 to 2, right? And we know the interest rate is 8% compounded annually. What do I need to do now?
We find the effective interest rate.
And okay, so I need to find the effective, and the effective is going to be so I sub A, because we want it to be annual, because my payments are in years, right? And so that's why we want I sub A. What should we do now? So how do I find it, in other words? Mazen?
Because it's compounded annually and the diagram is in years, we just put 1.08. We just use as chapter 2.
Exactly. So the interest rate in particular is just going to be the same. It's going to be 8%. I don't really need to use a formula here because already these two match, exactly like Mazen said. And in the formula, like Mazen said, it's going to be 1.08. So when I apply the formula, oops, let me erase that bit. You see here it's 450. And then I find f given p as before. I use my 8%, right? So remember this formula is just 1 plus 0.08. And I have 2 years, so I raised it to the power 2. Right? And so that gives me the future worth of this 450 at time period 2. And like I said, we're going to add the 150 to it, right? And so we get this value here, the 674.88. Now, of course, what's left, like I said before, is I need to take this and I need to move it here. And so I do a similar thing, except now there is a difference. Now the interest is compounded monthly. It's not the same as the yearly payments that I have. And so in this case, I need to actually find I sub A. And the way I do it is by applying the formula. And so let's see really quick what the formula says. The formula says I divide by CK, right? I divide the nominal. The nominal is 6%. I divide by CK. I raise to the power C. And so here, notice that my payments are in years. They're annual. So K is actually equal to 1. Right? As we said before, if it's annual, K is equal to 1. C is how many times I apply the interest. And you notice here it says compounded monthly. So I'm applying the interest 12 times a year. So my C is equal to 12. And so I plug in, I divide by 12, and then I raise to the power 12. I get my interest rates using the formula. Now I do the same thing as before, but now I use this interest rate instead of a given 6%. So this is what goes into the formula. And of course, I have 2 years, right? And so now remember, this interest is annual, and my years are annual also. They're in years, so they match. So I put in my 2 here. And then I add the 450 at the end, and I get the future value. All right, so hopefully this is clear to everyone. If you have questions, please don't hesitate to ask. There is another practice problem here, which does pretty much the same thing. It's just going through different variations of the compounding period, right? So quarterly, monthly, continuously, but it's the same exact formula. So I'll skip these just in the interest of time. I don't want to waste your time going over the same sort of example 4 times, right? But it's the same thing. You find the effective interest rate, and then you use the formula. You find the effective interest rate, and then you use the formula that we've been using before. And if it's continuous, you're going to use its own formula, right? Which is e to the r divided by k. This example is kind of nice. So some of you are heavy coffee drinkers. Maybe you guys drink 1 cup of coffee or 2 cups of coffee a day. I certainly don't drink coffee a lot. And so it's asking, suppose instead of paying $2 a cup every day, or maybe $4 a cup if you drink 2 cups a day, or 6 if you drink 3, suppose you take that money and you invest it. So every day you set aside your $2 for coffee, you stop drinking coffee altogether, and you invest it in a savings account or something, right? That gets you some interest. It's asking, or it's telling you that after 50 years, here's what you would actually have, right? So these amounts here are what you would have after 50 years if you set aside your $2 a day, and the interest rate was 5.5% compounded weekly. It's assuming, however, that the price for a cup of coffee stays the same. It's constant across time, so there's no inflation here, right? So this is an assumption that this problem is making, all right? And so let's see how you can find a value like this. So remember that the interest here is compounded weekly, but I'm setting aside $2 every day. So in a way, if you think about it at first, my payment period is shorter than my interest period. My interest period is a week. Sorry, my table is wobbly. My interest period is a week, but my payment periods are days. And so what I can do is I can easily convert my payment period to match my interest period. How do I do that? Well, I know I'm setting aside $2 for a cup of coffee a day. Because I'm gonna have to wait until the end of the week for interest to be applied, I can just accumulate these $2 over the course of the week, right? So I can multiply 2 times 7 days a week to get $14. So this is effectively my what I'm paying in each week, or what I'm depositing in each week. So now my payment period is a week. My interest period is a week, but I have to still convert this nominal annual value to a weekly value, which we know how to do using the formula. And then I can proceed as before. So let's look at this case, 1 cup a day, and let's see how they got this value, 193,517. So again, assuming 1 cup a day, we follow the steps, right? And so first of all, we need to determine the effective interest rate. And actually, the first step is actually to determine C and K. But I mean, you can skip the first step and just go straight to the second step, because the second step assumes that you've already found C and K. And now, based on what I just said, the payment period is going to be a week, right? So in order to convert my annual, my nominal interest rate, remember R was 5.5%, but it was compounded weekly. I just need to divide by the number of weeks that I have in a year, right? And that gives me the effective interest rate per week. And so I know I have 52 weeks in a year, and so now I've converted my I to be per week. And so I'm good. Of course, I need to find the weekly deposit amount, make sure this is also per week. And so like I said before, it's just $2 every day, 7 days a week, and you're going to get $14 every week. And I find N. Remember, N is the total number of deposits. So if you're depositing this $14 every single week, so that's 52 weeks in a year, but you're making the deposit for 50 years. If you go back to the question statement, it's after 50 years, right? So make sure your N is 50. And now I can find my F given A just as before, but I use the correct interest rate, which I just found, and I use the correct N, which I've also computed. And I find the exact same value that was in the table. Okay? So now we're going to switch to a different part of this chapter, which talks about loan management or debt management. And the first slide here is actually just giving you an example of what happens when you don't pay your credit card balance on time. So if you carry a balance, which means you always have outstanding payments that you have to make on your credit card, and here I think it says this is the balance that they use to compute these values, right? And this is the interest rate. I'm not sure actually if this is like nominal or if this is effective. Not quite clear. It's in the book somewhere. I didn't look at it, to be honest. But here it's just saying that if you pay only 2% of your balance versus if you pay 4% of your balance versus if you pay 8% of your balance. Of course, if you pay more of your balance, that means first of all, it will take you less time. You see your time is decreasing to pay off that debt. And also the amount of interest that you would pay over a number of years is going to be less and less. So even though you increased, for example, the percentage of the balance that you're paying by 2% in this example, notice the reduction in time that it will take you to pay off that debt completely. All right, so this is just like motivating this part of the chapter. So now let's look at an example. So let's look at what actually happens in a loan when you take out a loan. Suppose you want a loan to improve your house, right? It's a home improvement loan. And you take out $5,000 from the local bank, and the bank tells you these are the terms of the loan, these are the conditions. I'm going to give you $5,000, so this is the contract amount, and you're supposed to be paying it back over 24 months. And your APR, remember, APR is nominal, so this is your R, it's 12%. And the bank needs to compute the monthly installment. Or maybe the bank doesn't tell you this what the monthly installment is, and you want to compute it for yourself. I mean, usually I think the bank is going to tell you how much you're expected to pay, but suppose for some reason they didn't tell you. So let's go over this example and let's see what happens. So first of all, cash flow. I mean, hopefully you're all comfortable with drawing a cash flow for this. It's a loan. I'm taking out the money, so this is money going into my pocket, $5,000, and then money going out every single year for 24 months. Sorry, every single month for 24 months, right? And so based on the steps, what I need to do in order to compute A, so my goal, my ultimate goal, is to do the following. I need to find A given P. And of course, this involves me finding I and me finding N. And so N is very clear here. N is 24. So that's easy from the cash flow diagram. What about I? How do I find I?
We need to find the C and K.
Exactly. So if you want to do it that way, let's see. So K, remember, is the number of payment periods per year. So how many of those do I have?
12.
Exactly. So K is 12. What is C? So C is the number of compounding or interest periods per payment period.
1, I think.
Yes. So each month, our payment periods are months here, as you see in the diagram. Each month, I'm applying interest one time. So C is 1. And I have 12 months in a year, so K is 12. And so I can just take this 12 and divide it by 12, and I get 1% per month. That's my effective interest rate. And you could have done this even without finding K and C, right? You could just say it's 12%. I want it to be months. I will just divide by 12. All right. So here's what we have so far. Now we still need to find A. So I will just use the formula for this. We have, so I kind of revealed the answer for you here. It's also here. So I have my P is 5,000. I need to find A given P. I use my 1%, and I know that N is 24 because I have 24 months over the course of the year, over the course of the 2 years that I'm paying the loan back during. And so I find that it's 235.37. Okay, so this is nothing new. This is kind of, again, an application of the formula that we've covered before. What's new is the following slide. So if I look at what is actually happening in the loan, and I'm not sure how clear this slide is, but I'll tell you what the components are, and you can look at the actual figures later if you want to. So you're going to make 24 payments. So this is just telling you the payment number all the way to 24. Each payment, as we computed, is going to be for 235.37. So as you see here, the size of the payment is just going to be 235.37 for the entirety of the loan, 24 months. A useful thing is to compute how much of this payment that you're making. Remember, when you pay off a loan like this, you're paying the principal and you're also paying interest. So you're paying two things. So if you want to compute what's happening with your payment, how much of it is going to pay off your principal and how much of it is going to interest. This is what this table tries to break down. So look here. So you see here the loan balance. Now at time 0, when you get the loan, your balance is going to be 5,000. That's how much you're expected to pay back. However, of course, you have to pay back some interest. And so if you compute 5,000 times 1%, you find out that it's $50. So that your interest on the unpaid loan balance is going to be $50. And that's what you see here. So that's the interest payment. What that means is, of this payment that you're making in the first month, $50 of it is actually going to pay off interest. The remaining $185 is going towards paying off the principal of the loan. And of course, after that, because this is going towards the principal, you can deduct. So you see here this 4814.63. So let's do 5,000 minus 185.37, right? So if you take your loan balance, so here I'm going to do times 0 here, right? So there's no payment, really there's nothing. It's just your loan balance at time 0 is 5,000. This amount here went towards paying the principal. So how much is your balance going to be after or at the end of time 1? Well, it's just going to be my original balance minus how much of my payment went towards paying off my balance. So if you do 5,000 minus this value, you're going to get this value here. And then you proceed in the same way, right? This is your balance at the end of time 1. How much interest am I expected to pay? So let me erase all of this stuff so you can see. Well, if you compute 1% of this value here, you will find exactly 48.15. So that percentage or that amount from your next payment is going to go towards paying interest, and then the remainder of this 235 is going to be going towards the principal. And again, you can compute your balance by subtracting. And you can see like how you can just proceed until the very end when your balance comes to 0. And you see here the percentage of your payment that goes towards interest is decreasing with time, and more of your payment is going towards the principal as you pay more and more installments for the loan, right? So this is a nice picture that demonstrates that. Time is going this way. So this is the first payment here, the bottom bar, right? And you see here $50, like we computed, is going towards interest. The remainder is going towards your principal. And you see all of these bars are the same because you're always paying $235 or whatever, I forget the number, $235.37 each month. So the length of the bar is the same. It's just that the proportion that goes towards interest decreases with time. And the likewise, of course, because I mean they sum to 1, the proportion that goes towards your principal increases with time. Okay, I don't think we have time to go over this example in detail today, but just to set the scene, I guess, for next class. Again, we have a loan, right? We have P and then we have A. And it's actually, this example is asking you for the following. Compute the remaining loan balance after making the nth payment. So just in general, I think the example later is going to ask for the loan balance after computing the 6th payment. So suppose I'm here, and like the example that we've seen before, I want to pay off the remainder of my loan here. So I want to pay all of this in one go at that point of time. How do I compute this? Okay, and so we're going to see that next class. We're going to go over this example and finish the chapter at the beginning of next class. And I think we're also going to have time to start chapter 4 in the next lecture. Okay, so I'll wait around for some questions. Other than that, I'll see you in 2 days, and I'll look into the quiz issues, and I'll see what to do about the average for the quiz. All right, thank you guys.